Measuring a complex industrial system in the mid-20th century required a massive, dedicated physical installation. Analyzing a single electrical signal meant using an expensive tool packed with rigid knobs and switches, each wired for a highly specific, unchangeable task. This hardware dependency limited medical education as well, where students shared scarce, costly patient monitors that recorded heart rhythms on continuous streams of paper tape. The virtual instrument disrupted this reliance on fixed hardware by moving measurement logic into software. A virtual instrument replaces specialized dials and circuitry with a flexible software platform, allowing users to configure tools through a computer. A single laptop can now emulate an entire room of legacy analog machines, performing the work of dozens of different dedicated tools. Transitioning from hardware to software removes the physical and financial barriers that previously kept advanced measurement tools out of reach for most researchers. Modern software allows a beginner to build a complete measurement system from scratch on a laptop. This simulation logic works by generating virtual sensor data through code. A random number generator produces fluctuating values, representing temperature, and plots them directly onto a digital graph. The system then applies automated logic to this data stream, using a greater than block to compare every new value against a fixed safety limit. The moment the simulated data breaches that limit, the logic path completes, instantly triggering a red warning indicator. While the logic works perfectly in the background, raw data points and code blocks are difficult for a human operator to interpret during a crisis. The user interface serves as the essential bridge, translating these digital calculations into clear, actionable information for the operator. Effective dashboards rely on simple layouts, consistent visual language, and intuitive indicators to ensure the operator never has to guess what the data means. Clean UI design functions as a mandatory engineering safeguard, reducing cognitive load to prevent human error when monitoring high-stakes systems. This exact same virtual software logic now moves seamlessly from the basic student laptop into high-pressure clinical training environments. Medical schools use virtual platforms to recreate the complex displays found on professional healthcare monitors. This allows students to practice reading critical bioelectric signals, like an ECG, in a risk-free virtual space before they ever touch a live patient. The scale increases again on the automated factory floor, where massive machines operate under the exact same digital principles. The threshold logic used in a basic simulation is the same logic governing these enormous industrial systems. Industrial dashboards monitor thousands of physical sensors at once, watching for dangerous fluctuations in pressure or pipeline flow. When a sensor detects a pressure spike, the virtual instrument executes an automated countermeasure, instantly signaling a shutoff valve to prevent a catastrophic failure. From the industrial valve to the student's laptop, the underlying software remains consistent and universally scalable. This technology democratizes advanced training and system control, making high-level engineering accessible across multiple industries. Today, the ability to monitor and control the physical world rests on the precision of digital design, moving the limits of innovation from a hardware budget